Today we're going to look at exponential growth and decay models. So we're going to see if we can use those solving exponential equation into the word problems. Here we need to remember this growth and decay model will be using based on form of ft equals to a sub 0 times e to the kt exponents, or you could also say a equals to a sub 0 times e to the kt exponents, where you're going to use a as the amount of the time t so amount at the time of t, and P is going to be the principal, which is going to be original amounts as A sub 0. And then K is going to be growth rate. So K is the growth rate. We know T is the times. A sub 0 is going to be original amounts, starting amounts, right? And then A is going to be amount at the time of T times later. Okay, so that's the important formulas that you need to remember. So that's the format of the formula we're going to use when it's dealing with exponential growth and decay. So first example we have is U.S. populations. So from 1970 to 2007, this is the growth of the U.S. populations in millions. So 1970, you had 203.3 million populations. 1980, you have 226.5 millions, and so on. The last measurement you have is 2007. Population was 300.9 millions. With that in mind, they want you to find the exponential growth functions. So we wanted to build the equations from this given informations. And then second, once you have the formulas, then they want you to find out which year will the U.S. population reach 315 millions. So in order to do that, in order to solve B, we need to figure out the A part first. Okay, so what I'm going to start with writing down all that information. So again, we're going to replace it into A equal to A sub 0 times e to the kt exponents. So let's see what information we have. We have a starting amount. So we have a time. How long this data is times. Well, it starts from 1970 to 2007. So when we do the subtractions of it, you get 37 years. So that's the one information we have. And then we know that K is the rate. And we don't know the rate yet. We have a data, so we can figure out the rate using those data given. So that's what we are trying to figure it out. And then we have A, which is going to be after 37 years, your population was 300.9. And then we have A sub 0, which is the starting population for this example, which is going to be 203.3. So when we replace those values into the equations, we have 300.9 equal 203.3 to kt, and t is 37. K, which is x, right? X. And when we're solving that, I forgot to write e there, right? We wanted to divide both sides by 203.3 first, so that you will leave on the right side with the exponential form only, right? And you will have then 300.9 over 203.3 equal e to the 37 x exponents. And then in order to solve for x, trying to bring down exponents the bottom, right? So you're going to multiply both sides by a natural logarithm to bring down the exponents. This will give me then 300.9 over 203.3 equal 37 times x times ln e. And we also know ln e is equals to 1. And it means that if you wanted to isolate x, so for x, you need to divide both sides by 37. So which your x should be ln 300.9 over 203.3 all over 37. And when you plug in that into the calculator, you're going to get somewhere close to 0.011, which this is going to be your rate. With that rate, you should be able to build the equations, which is going to be A equals to 203.3. So your ending amount A will be changed, depends on the time, how long that you're looking at it, right? And then K is the rate that we just found, and time is another fact that it could be changed. So this is going to be formula for this given problems. That's A part. And if we wanted to find out the B, right? So let's close that off. And if we wanted to find out the B, then we're going to replace. Question is, by which year will U.S. population reach 315 million, right? So that T is what we're going to try to find out. So on that formulas, we're going to replace 350 million, but we're trying to still looking for the time. So we're going to divide both sides by 203.3. And then you're going to multiply both sides by a natural logarithm so we can bring down the exponents. I will get ln 315 over 203.3 equal 0.011 t and the e exponents, because these two cancel out, right? Which this is going to be 1. So your t should be natural logarithm of 315 divided by 203.3 all over 0.011. And this come up to be close to 40. So the amount that it started, this amount right here, right? This amount started 1970. And when you're adding 40 years from that beginning year, you get about 2010. So year 2010 is when your population will become 315. Okay, second exam that we're going to look at it is going backward. The other problem that we were looking at it, population, we were looking at the future amounts, future of U.S. populations. This time, example 2, we see if we can tell the age of old stuff. And here we have an example of carbon-14. So this is the something that we can tell the age of the old stuff. And it say use the fact that after 5,715 years ago, amount of carbon-14 will have decayed to half the original amount to find the exponential decay models for carbon-14. So this is the example on the carbon-14. So using this example, we should be able to come up with the formulas, right? And then using that formulas, we're going to see if we can tell the age of that sea scroll. Okay, so let's start with the creating a formula first. So again, we're going to use the formula of A equal A sub 0 to the E to the KT exponents. And the original amounts become half, right? Because it's say half the original amounts, we could say that's going to be 1/2 or 0.5. And it means that your original is going to be 1, right? So you could say A naught is equals to 1. And A is going to be 0.5 or 1/2, right? Half. And then what else do we know? We have year of, that's the year of 5,715. So when we replace that, let's see what we have. We have 1/2, 1 time e to the 5,715, and trying to figure out x with that given information. I'll find out the rate of that given informations. And then this is same as 1/2 equal to e to the 5,715x. So you multiply both sides by natural logarithm to bring down the exponent. You get natural logarithm of 0.5 or 1/2 is 5,715x and ln e, where ln e is equals to 1. So in order to solve for x, you're going to divide both sides by 5,715. So your x is natural logarithm of 1/2 or 0.5 is okay to use it over 5,715. And when you plug in those numbers into your calculator, you will get negative 0.00012 about. So that's going to be your rate. This is going to be your rate. Okay, right? So then you can create a formula using that. So the future amount can be changed. And your starting amount was 1 e to the negative 0.00012 t will be the formulas to use, right? And now the second part of the question said that, trying to find out the Dead Sea Scrolls age when carbon-14 was only 76% remaining or containing, right? So then your amount A is going to become 76%, change to decimal will be 0.76. And e to the negative 0.00012 t. In order to solve for t, multiply both sides by natural logarithm to bring down the exponents, right? And natural logarithm of 0.76 equals to negative 0.00012 t, natural logarithm of e. And then you're going to divide that by the rate. So that you will isolate by t, where your t is going to be 2,287. So your age of that sea scroll will be 2,287 years before 1947.